Okay, so chapter 6 is where we are going to talk about systems of equations. Specifically, we're going to talk about systems of equations in two variables in this section. And we're going to learn lots of different ways to solve them. And hopefully, none of it is brand new material. And hopefully, it's maybe a little bit dusty, but it's not brand new. So a system of equations is composed of two or more equations considered simultaneously. So instead of just thinking about one equation at a time, we're going to think about it as a whole system. So if an answer doesn't work for one of the equations, then it doesn't work for the system. Like I said, that we're only going to consider two equations today. You can consider three equations at a time and three variables, or four equations, and so on and so forth. And the first way you're going to learn how to solve a system of equations is solving it graphically. So when it comes to solving graphically, you're going to graph both of the lines on the same Cartesian coordinate system, and you're going to see if they cross or not. Because what we're going to see is that there's really three different types of systems. There's ones that cross in one location, there's ones that never cross, and there's ones that lay right on top of each other. And so those are the three different styles you can have. Solve graphically. A system of equations generally has one curly bracket on the left-hand side, and then however many equations you're considering lumped together inside. In the Pearson site, I don't believe they use a curly bracket. They just give you both of the equations. I guess I'm a little old school in that I like mine bracketed together like this. That's how I grew up seeing them. So that's how I'm going to present them. So we're going to solve graphically. And if you remember back to our chapters where we solved using graphs, or we solved our equations, the easiest way to graph a line is to get it into y equals mx plus b form. So that's what I'm going to do. Neither of these equations are in that, so that's what I'm going to start with. That top equation, to get it into y equals mx plus b form, I need to subtract the 5 over and add the y over to move them around, so that I get y equals, I move the 5 this way, I move the y this way, x minus 5. Now it's in y equals mx plus b form. The bottom equation, I just need to move my 2x over, so I'm going to subtract it. So I get y equals a negative 2x plus 1. Now they're both in y equals mx plus b form. So now I'm going to graph them both on the same Cartesian coordinate system, which I'm going to hand draw, because that's what it is here. This is where you hit Kelsey up for her note cards.
I know, I left mine at home.
On the one day we graph.
I know.
Goodness. All right. So that top one, my red one, has a y-intercept of negative 5. So I go 1, 2, 3, 4, 5. What is the slope for that top equation? 1. So I go up 1 over 1. Up 1 over 1. There's the first line. Second line, the green one, or my bottom one, has a y-intercept of positive 1, and then a slope of what? Negative 2. So I'm going to go down 2 and to the right 1. Wow, my little marks are pretty dang good. I'm just going to say that. So I graphed them, but that doesn't tell me anything until I look at where they intersect. Where they intersect is actually the solution to the system. And they cross right here at 2, -3. 2, -3 is the solution to the system. I could plug in 2, -3 into this top equation and I would get a true statement. I could plug in 2, -3 into the bottom equation and I would get a true statement, because this is the only ordered pair in the known universe that actually works for the system. So where the two lines cross is the solution to the system. And I lucked out that my tick marks are actually really good, and it looks pretty dang on here. My one in my notes is even better because I had graph paper. Are there questions on how you do this? Okay, so I kind of alluded to the fact that there's actually 3 different types of systems of equations. And here's how they look in general formats. The one we just did, where it crosses in one point, is known as a consistent system or independent system. There's exactly one solution and one solution only. One thing you can note about this system is that the slopes are going to have opposite signs. You have to have a positive slope and a negative slope in order to have a consistent system. If you have 2 positives or 2 negatives, you're not going to have a consistent system, like just straight out of the gate. So if you write them both in y equals mx plus b, and you notice that they have opposite signs on their slopes, you know you're going to have a consistent system before you graph it. Another type of system that you can have is one that's made up of parallel lines. Parallel lines never cross, which means there's not going to be a solution. Parallel lines have the exact same slope. We know that from previous sections. This is known as an inconsistent system. So consistent system has one solution, inconsistent system has no solutions. The last one is known as a dependent system. I don't know why I wrote consistent again. Not sure why I wrote consistent again. But it's a dependent system. This is where your lines actually lay directly on top of each other. And because they lay directly on top of each other, they have infinitely many solutions. Everything is in common. So these will have the same slope as well. Same slope, different slope. The difference between the bottom two is if you are dependent, you're going to have the same y-intercept as well. If you are parallel, you have different y-intercepts. When it comes to Pearson, when you go to graph a dependent system, if you discover that you have a dependent system but you're asked to graph it, you will only graph line one time. You're not going to graph it and then graph the same line right on top of it yourself. It won't let you do it. So just know that if you have a consistent or an inconsistent system, you'll graph both lines. If you have a dependent system, you will only be asked really to graph one line because it gets repetitive graphing the same line on top of itself. Questions on these? We good for me to flip? Okay. All right, so that's graphing. That is not the most user-friendly way to solve a system of equations. There's 2 other methods that are way more user-friendly. One is known as the substitution method. The substitution method is where you're going to solve one of your equations for one of the variables. Then you substitute that into the other equation, solve for the remaining variable. Then you're going to back substitute the answer you just got into the original equation and solve for your last variable. And the last step is always nice to check your solution We won't check all the solutions today, but that is a good last step regardless. These steps will make a little bit more sense when we actually solve one. But the substitution method is a nice method to have. Okay, so we have our system, which is actually the same system you guys just graphed. I did that on purpose because you already know the answer to the system. Graphically, we found that the answer was 2, -3. So that better be what we get whenever we use substitution. Step 1 says we need to solve one of the equations for one of the variables. You get to pick. You get to decide if you want to solve for x or for y and which equation you want to use. There's no right or wrong on this. Regardless of which way you go, it will still work. I generally will pick a variable that doesn't have a coefficient and one that is positive. So if I was looking at these two equations, I would either solve my top equation for x, or I would choose to solve my bottom equation for y, because it's not going to take much algebra to move that stuff over and get it to where x equals something or y equals something. Which would you prefer? Top equation x or bottom equation y? Top equation x. So to get x by itself, what would I do? Yeah, add the y over. That way I get x equals y plus 5, or 5 plus y. It doesn't matter. But now that I know what x is, I'm going to take all of this, because this is all that x is, and I'm going to substitute it into my second equation in place of x. So instead of 2 times x, I'm now going to have 2 times y plus 5 plus y equals 1. So I wrote the equation exactly as it was, but instead of having x, I substituted in the y plus 5. Now I have one equation with one variable. I can solve one equation, one variable. I can't solve 2 equations, 2 variables. I've got too many different unknowns. But now that I only have one equation with one variable, I can do this. I can distribute my 2. I can combine my like terms of y, where I have 2y and 1y, which is 3y. Subtract my 10 over. And divide both sides by 3. And I find y is -3. So that was step 3. I solved for the remaining variable. Step 4, you back substitute your answer into one of the original equations. Now that I know what y is, I can plug that in right here to figure out what my x is. Because x is y plus 5. So y is -3 we just found, plus 5, meaning x is 2. So I have 2, negative 3, which we already knew because we had done this equation, or done this system graphically. Had you decided to solve the second equation for y and find y first and then back substitute for your x that way, or back substitute up for your y, you would still get the same ordered pair. You just get it in you'd find your x first and then you would find your y. But you'd get the same values. If you get down to the point where you have y equals or x equals something, don't just stop. You're not done. You've only found half of your ordered pair. And when it comes to Pearson, it's going to ask you to type in an ordered pair when you find an ordered pair. But what do you have to have an ordered pair? You have to have an x and a y. What else? Parentheses. That is key. If you don't put parentheses and you put 2 comma negative 3, you didn't give me an ordered pair, you gave me a listing of numbers. And it will count you wrong every single time. So make sure you put those parentheses in there so you don't miss the points. And then step 6 would be check your solution. Like I said, I'm not going to do that every time. I did it in my notes though. The way you check your solution is you plug in the ordered pair that you got into both of the original equations and make sure that you get true statements. If you get a false statement, then either you did your algebra wrong here or you did your algebra wrong up here. Questions? Okay, that's the substitution method. The other method we're learning today is known as the addition or elimination method. Your book, I think, refers to it as the elimination method, and I've always learned it as the addition method. It means the same thing. To do the addition or elimination method, you want to get both of your equations in your general form, which is ax plus by equals c. Then sometimes you're going to have to multiply one or both of your equations so as to eliminate one of the variables when you add your 2 equations together. Step 2 sounds weird. It makes a lot more sense when we see it. What happens is once we do step 2, we end up with one equation with one variable. If we can solve that. Steps 3, 4, 5, and 6 of our addition elimination method are the exact same steps as our substitution method. So it's only steps 1 and 2 that are different. Step 3, we solve for that variable. 4, we back substitute it into the original equation. 5, we solve for the last variable. And 6, you check. One thing I'll tell you about the Pearson site, it's a computer program. If it asks you to do it in the addition method, or if it asks you to do it with the substitution method, the computer's not going to know how you got to your ordered pair. You could graph them all, and you could get your ordered pairs. So I let you know that kind of up front, in that if the addition method makes more sense to you, use it. If the substitution method makes more sense to you, use it. When it comes to the paper and pencil exams, you're going to need to follow the instructions. If I tell you to use the addition method, I want you to use the addition method. If I tell you to use substitution, you're going to want to do that. The one thing about the Pearson site is if it asks you to use the addition method, generally, that's the easier of the 2 methods to use. So it's not just trying to be difficult. It's actually telling you which one works best. And I say works best because sometimes you're going to end up with fractions if you use one method over the other. Like you're going to play around with fractions, not that your answer is necessarily going to be fractions. And while that's totally fine, I don't know about you, I'd rather play around with whole numbers than play around with fractions the whole time. So, just so you know that. Let's see how this looks. I'll try and keep the instructions up there. So use the addition or the elimination method to solve this system of equations. 2x plus y equals 2 and x minus y equals 7. Step 1 is to get both of your equations in ax plus by equals c form. Really what you're focused on is you want your x's to line up, your y's to line up, your equal sign to line up, and then your answers to line up. And as long as that happens, then it's in the right format. This one came in the correct formatting. Because here's what we're doing. We're doing vertical addition like you did back in grade school. When you first learned how to take 12 plus 13, you did vertical addition just like this, didn't you? And you added your ones column and you got 5, and you added your tens column and you got 2. That's what we're doing with equations. But we want one of our variables to fall away. We want one of them to disappear. That way we end up with one equation, one unknown. So what you want to look at is if it's already lined up, which this one is, then we're going to go to step 2, where maybe we're going to have to multiply one or two of the equations by a constant. But before we do that, let's look. If I add them right now, will my x's go away? No. Will my y's go away? Yeah, because I have a positive y and a negative y, and if I add those together, I get 0. So I don't need to do step 2 at all. I just need to add. So I'm going to do a big, giant addition line, and I'm going to add straight down. I'm going to add my x's, add my y's, and add my constants. So I have 2x plus x is 3x. My y's fall away, and 2 plus 7 is 9. Now I have one equation with one variable. I can solve that. Divide both sides by 3, I get x equals 3. So then I take this, and I plug it into either one of the original equations and solve for y. It doesn't matter which one. I'm going to plug it into equation 1, the top one. If you want to check to make sure that I'm telling you the truth, you can plug it into the second equation and make sure we both get the same y's. So in place of the x, I'm going to put a 3. Did you get negative 4? Cool beans. Me too. So that means my ordered pair would be 3, negative 4. And we could test this. We could plug in those values and make sure that that did work. I did not test it, but we could have. You could solve it using the substitution method, make sure you get the same answer, or you could graph them and make sure that you get the same answer. All of those are good checks for making sure that you did it the correct way. But this one is obviously the easiest one because it gives it to us already nice and lined up. It was already ready to add. One of our variables canceled. We were good to go. Obviously, they're not all going to be quite so nice. So we're ready to see a slightly harder one? Solve using the addition or elimination method. I was actually nice, and all of them today automatically are lined up. So you don't have to do any manipulating. But they could give it to you where like y equals mx plus b form, and then you have to move it around. None of them that I did, though, I make you do that today. That being said, though, this one isn't as nice as the last one because if I add my x's together, I still have an x. If I add my y's together, I still have y's. So none of them are going to just eliminate if I do my addition straight out of the gate. So this is where we will have to apply step 2, and we're going to have to multiply one or both of these equations by a constant to get them to go away. So there's no right answer, but would you like to get rid of your x's or your y's? Okay, if we get rid of our x's, we have a coefficient of 4 and a coefficient of negative 5. So what is a number that 4 and 5 both go into? 20. That's great. So what do I need to multiply 4 by to get to 20? 5. So I'm going to multiply this whole top equation by 5. The entire equation, not just my x term, the entire equation. And then I do a similar process for my bottom equation. And the nice thing is because you chose the x, it already had opposite signs. You had a positive, then you had a negative, so we don't have to multiply by a negative. It's not a big deal if you did. It's just one less thing we have to worry about. So I'm going to multiply the whole top equation by 5, the whole bottom equation by 4. And then I'm going to do my addition, because now when I add, my x's will go away. I get 15y and 8y is 23y. 115. I'm going to guess 5. Y is 5. Y being 5, I plug that into either of the originals. And I always say go back to the originals and don't go to one that you've multiplied by something. And the reason for that is if you made an error in that multiplication step, you're not going to notice it. So plug it back into one of the originals. I'm going to plug it into the bottom one. And we get negative 1, 5 as our ordered pair. And we could test that. We could plug in negative 1 and 5 into both of those equations and make sure we get true statements. And it's kind of nice that you picked to eliminate out the x, because on my notes, if you look at them, I eliminated out the y first. So when I multiplied my top equation by a negative 2 and my bottom equation by a positive 3 so that my y's would be opposite signs. And then I got through them that way. I eliminated out my y's first and got my x value and then plugged it in and solved for my y. Got the exact same answer. Are there questions? Okay. We're going to do 2 more. X minus 3y equals 1 and negative 2x plus 6y equals 5. If I add them together, neither one disappears yet. So do you want to get rid of your x's or your y's? Y's, okay. So I have a negative 3y on top and a positive 6y on bottom. What do you think we should do? Like, what's a number that both 3 and 6 go into? That's true. 6 is also one that they both go into. I know, we're getting there. We're getting there. We're getting there. Don't jump ahead. If we multiply the top equation just by 2, then we'll have a negative 6y. So sometimes you don't have to multiply both, okay? Sometimes you can just multiply 1, and that'll allow you to eliminate out. Now, some of you guys are already cheating a little bit, and you already see what's going to happen. But that's the big thing there, is you don't have to multiply both. If you were to take them both to 18, it would still work out, okay? Or if you took them both to 12, it would still work out. But I'm going to have 2x minus 6y equals 2. And I wrote it right beneath the bottom equation so that I can just go ahead and do my addition, where I'm adding the black one and the red one. Negative 2x and positive 2x means my x's go away. 6y minus 6y means my y's go away. So I have 0 on the left-hand side. And on the right-hand side, I have 7. Does 0 equal 7? This is false. What do you think that means? No solution. So what does that tell you about these lines? That's right. These are parallel lines. There is no solution. If you were to graph them, they would run side by side. So this is what this looks like as you're trying to solve these. What happens is both of your variables fall away, but you get a false statement. This is an inconsistent system. So that kind of alludes to what the next one's going to do. 2x plus 3y equals 6 and 4x plus 6y equals 12. Would you like to get rid of your x's or your y's? Do what? You can. That's the same as multiplying the bottom equation by half. Yeah. We could. But then if we add them together, it's still not going to do anything. That's true. This is why I don't usually put them side by side like that, because then you can tell. So yes, if we multiply this bottom equation by a half, which you are totally allowed to do, you'll get 2x plus 3y equals 6. And as you can tell, those are the exact same equation. So what do you think that means? Infinitely many solutions. So this is what it looks like, though, if you actually work through it. Because sometimes, if it's not written right on top of each other in the ax plus by equals c formatting, you might not see it straight out of the gate, like you did here. And if you don't see it straight out of the gate, let's pretend like we didn't, we would have multiplied like the top equation by a negative 2, and then when we add them together, both of our variables go away, but we get a true statement, because everything goes away. We get 0 equals 0. That's always true. And because it's always true, we have infinitely many solutions. So if you get a false statement, it's no solutions. Infinitely many solutions is an always true statement. All the rest of them are going to be those consistent systems where you get an ordered pair. Are there questions on how these are? So let's go to the handout. If you didn't pick up a handout when you came in, you probably want one now, because these are the word problems. I made the handout so you don't have to write down all the words, because I am nice. These are word problems that are much easier to solve using systems of equations. In your book, they use a table sometimes, and other times they don't. I've taught this for over a decade, and some students love tables, some students hate tables. So I will try to show you both ways as I can, and you can pick which method you like. For our first example, we have Max's Munchies. At Max's Munchies, caramel corn is worth $2.50 per pound and is mixed with honey roasted nuts worth $7.50 per pound in order to get 20 pounds of mixture worth $4.50 per pound. So how much is each snack, or how much of each snack is used? So we don't know how much caramel corn we're putting in or how much of the roasted nuts, but we know we're going to get 20 pounds of the mixture, and we know the price of each of these individually. Okay, lots of stuff that we know. But from this, we need to get a systems of equations. So I'm going to show you this one with a table, and I'm not going to do the others with a table. That's kind of my trade-off here. And so you can determine with this problem if you like a table or not. So if you decide to use a table to organize this information, you have your types of snacks in the first column. We have our amount. we have our cost. And I guess I made a really big table and didn't need it to go quite so far. Or a price, I guess you could call this price. And then you would have like your total or your value, however you want to think about this last one. So our first snack is our caramel corn. I'm going to call it CC for short. And we have our nuts. And then we have our mixture. Now, from our information, we don't know how much of our caramel corn or our nuts. That's what we're trying to figure out, right? Those are the two unknowns. So I'm going to call caramel corn X and nuts Y. You can call them A and B, you can call them C and N, you can call them whatever you want to call them. I'm going X and Y because that's what we generally use in math. Do we know how much of the mixture we should get? 20 pounds. Okay. Now we do know the cost of all these things. We know that caramel corn is $2.50. We know that the nuts are $7.50. And we know that we want the mixture to be $4.50. The way we come up with our total is you take your amount times your cost. You multiply across your row. So my total would be 250x, 750y, and 450 times the 20 pounds. And you're like, okay, cool, I have a table. I don't see any equations. Your equations come straight out of your table. Equation 1 comes out of your amounts. Equation 2 comes out of your value. Equation 1 will be x plus y equals 20 because the pounds of caramel corn added to the pounds of nuts have to equal the 20 pounds of mixture. And then we have our cost, our value of each of these things as well, has to equal the total cost or value of our mixture. Now we have two equations, two unknowns. We have our system. And you could use whatever method you want to use. I will say in general, most of the time, I would go with the substitution method because I don't want to multiply that top equation by 2.5 or 7.5 or whatever. So I would solve for my x or my y and substitute. So if I'm solving for x, I would subtract that y over so that x is 20 minus y. And then I'm going to plug that into my second equation in place of my x. So 2.50 times 20 minus y plus 750y equals 90. 450 times 20 is 90. Distribute your 250. You get 50 minus 250y plus 750y equals 90. 5y equals 40. So y equals 8. Another reason why I like the table method is because at this point, I just found something. And instead of me having to go backwards in my systems and figure out what in the world y equals, I go up here to my table and I say, oh yeah, y was the amount of nuts. I need 8 pounds of nuts. And then either you can use your table and to come up with how much caramel corn you need, or you can plug this that you just found into the equation, where you have 20 take away 8 will tell you the amount of caramel corn that you need, which is 12. You need 12 pounds of caramel corn and 8 pounds of nuts. When it comes to mixture problems, I really like tables, and some of you might not. And if you don't like tables, the way that you would approach this problem is you would start with the amounts. You'd start with coming up here with your x plus y equals 20, because they will always give you enough information for you to come up with that one. Where you don't know how much of the 20% solution to add to the 30% solution to get a 15% solution. Like, you're always going to know, so you're going to have, okay, well, I have X amount here and Y amount here, and I have to get to 7 liters here, or whatever. After that, what you do to come up with the next equation is you take your amounts times their cost, or times their strength, and that gives you the second equation. Because notice we have the same equation. We have X plus Y equals 20. It's just now we put their costs in front of them. And that's how you get your two equations if you don't want to use a table. Questions? Okay. I think we can get through at least one more, maybe two more. There's only 2 left. If we don't get through this last one, we can talk about it on Friday if we need to. All right. Dyer's Office Solutions offers sales representative a choice between getting paid a commission of 8% sales or being paid a monthly salary of $1,500 plus commission of 1% sales. For which amount of monthly sales do the two plans pay the same amount? All right, so here's what we know. We're going to get paid, and the pay is salary plus commission. That's what it is. And you might be like, well, one of them didn't have a salary. You're right, so the salary would be 0 in that case. So the first plan offers a pay of 0 salary and just 8% commission of sales. When we talk about percentages, we always change them to decimals, and we don't know the commission because we don't know how much they're going to make. So it's dependent upon how much they sell. The second one, the pay offers a $1,500 salary and then a 1% in sales. So a much smaller percentage of sales, but you are at least guaranteed $1,500 that month. The first one, if you sell nothing, you get nothing. For what amount of monthly sales do the two plans pay the same amount? What do you think we have to do? That's right, we set them equal to each other. We'll have 0.08x equals 1,500 plus 0.01x. And we're going to solve. I'm going to subtract that penny x over. I would divide both sides by that 0.07 and find that x is $21,428.57. So if they sell, whoever sells, at least $21,428.57, then the salaries pay the exact same amount. If you took Math 20, I know for a fact that one comes up. The mixture problem comes up in Math 20 as well, almost verbatim, word for word. If you didn't take Math 20, you didn't miss much. All right, we still got 3 minutes. We can do it. Concert tickets. Here we go. Ready? One evening, 1,500 concert tickets were sold for the Summer Jazz Festival. The tickets cost $25 for a covered pavilion seat and $15 for a lawn seat. The total receipts were $28,500. How many of each type of ticket were sold? Okay, we've got lots of information. We know that we sold 1,500 tickets. We know that some of them cost $25 and some of them cost $15. And we know that we had a grand total of $28,500 in sales that day. Now, we don't know the rest of it. We don't know how many of each. So let's call one of them X and one of them Y. That's kind of our default. So think of this a lot like we did with the snacks. If we sold X amount at 25 and X and Y amount at 15, how many total did we sell? How many total tickets did we sell? 1,500. So if I sold X at $25 and Y at $15, I know grand total I sold $1,500 or 1,500 tickets, excuse me. To get my second equation, I'm going to take that exact equation but put the costs on it. Now, this last little one is going to change a slight bit because I don't have to do up here at my nuts and stuff. I didn't have my grand total, but I knew I had this many times this, okay? Here, I know my grand total. So I'm not going to have 1,500 times something. I'm just going to have the 28.5. So how much was a X ticket? $25. So I have 25X. How much was a Y ticket?
15.
And then total, I sold $28,500. There's my system. Again, I would recommend solving this using a substitution. You don't have to. You could easily multiply that top equation by a negative 25 or a negative 15 and doing it that way. I always ended up using a substitution. And when I use substitution, I find that I sold 900 lawn seats and 600 pavilion seats.